Okay, so today I'm going to talk about Robot Raconteur, which is a middleware, and PyRI, which is a teach-dependent programming environment. So I'm going to have to go pretty fast because there's a lot of material to cover, but we're going to hold follow-up webinars. Hopefully these dates will hold. They might be tentative, so stand by on the actual time. So we're going to reserve 2 hours. The first hour will be presentations and questions, and then the second hour will be demonstrations and further questions. So if you only come for 1 hour, that's fine. We'll do all the main presentation in the first hour. So I want to start by thanking the contributors to these projects. RPI is the biggest contributor. I've been working with them since I was a student, and Robot Raconteur began when I was a student in the lab there. I also want to thank Southwest, General Electric, and Raytheon for participating in projects, and ARM and New York State for funding them. So they provided funding over the last couple of years for these projects. So the motivation for Robot Raconteur starting in 2010 was we had lots of different devices in the lab, and there was really no good way to integrate them together. And we were using MATLAB and Windows and XPC Target and a bunch of other different equipment, which is not really, well, at that point it wasn't ROS friendly and still is not really that often used. So the goal was to develop a system which would prevent a lot of boilerplate from being generated for each project. And the other thing is the people in our lab are not software engineers, so it had to be very easy to use, or it would not be possible for them to use it. So the main motivation is actually my PhD project. So this is a micromanipulation system to assemble parts on the order of micrometers. So this part that's being manipulated right now is 300 micrometers by 200 micrometers by 25 micrometers. So it's a very small part. Just barely visible at the naked eye. So we're using probes here to manipulate the part and assemble it. And this is a very complicated system, 24 actuators, 4 cameras, FireWire cameras, USB cameras, auxiliary actuators, joysticks, multiple computers. And this is being done in Windows, MATLAB, XPC Target, a whole bunch of different proprietary drivers. And this is just taking too long for me to keep everything coordinated. So Robot Raconteur was developed to help solve this problem and grew from there. So the overview of the system, it's a language platform, a transparent independent communication framework. This is designed to be plugged into other products and used in any available platform. It works on many platforms, 7 languages, and 6 transport technologies. It uses a client service model. So this is an object-oriented system. So a service will expose objects that a client will talk to. The object-oriented nature allows it to be forward and backwards compatible using polymorphism. So we have very structured interfaces which can be added to in a very structured manner. So you're not worrying about tracking which functions are available. It's fully plug and play, meaning that when you connect to a device, it gives you its information at connection time. So it will generate this proxy automatically. If you connect from MATLAB or Python, it'll tell the service, tell the client how to communicate with it. So you don't have to do any prep work. You can just immediately use the interface. You can either do request response streaming or most recent data. So it has semantics for the different types of data that a robot would use. And it also has data types specifically designed for automation systems. It has TLS, certificates and password security, has its own centralized certificate authority, so that any device which has a certificate from this chain can communicate and authenticate. And these certificates are available from me at nominal cost. It's compatible with web and cloud without any proxies. So any device can accept a connection from a browser using WebSockets with security, obviously. And any device can talk to a server running HTTP with WebSockets. So you can connect to a web server, like an ASP.NET server can actually run Robot Raconteur internally and accept connections from devices. It has notice service discovery, long-term compatibility. You can connect to device from 2010 still with modern clients. It's open source, open standards, and the core library is available in ROS Noetic and ROS Humble, although ROS Humble isn't synced yet, so the binaries aren't there yet. There's also a Robot Raconteur to ROS2 bridge. You can access ROS2 topics and messages using a lot of the plug and play features through Robot Raconteur. There are many examples, which I don't really have time to dwell on. There's human-guided manipulation, cooperative robotics. We used it for building control for lighting, assisted robotics. This is a project using a mobile robot with a Baxter on it to work with a disabled person, composite layup, and stretch robotic cooperative robots. And you can actually run Robot Raconteur on an Arduino Uno 2 kilobytes of RAM using Ethernet shield. And this is actually supports Discovery and WebSockets. So it's just a tech demo to show that you can run Robot Raconteur on extremely limited devices. And the source code is on GitHub. Here's our primary test bed. This is from the ARM project. So this is a real-time manipulation using these robots. These robots are using Tesseract to do collision checking. And there's a real-time controller we developed, which is able to avoid collisions while using vision feedback to place items in trays. And this is Ed RPI who did the work on the experiment. So this is a diagram of what Robot Raconteur looks like. You have objects you want to talk to in the service, and the service generates the proxies in the communication channel to create references on the client. So the client can use these objects as if they were local. The service definition file is an IDL which describes what was contained in the services. And all of these request response support try-catch error transmission, so you can just throw an exception, it'll show up on the other side automatically, which removes a lot of boilerplate code to do that. So this is just kind of a walkthrough of how it works, but I'm going to skip this for time. So there are two main ways that the system is plug and play. The first is dynamic type and proxy handling. So for MATLAB and Python, you don't need to have any knowledge beforehand of the types on the service to automatically generate them. You can also have interoperability through standardized service definitions. So these are common types which allow a production system to know how to talk to specific classes of devices. So deployed systems will require standardized types so that clients which are designed for a certain type of device will be able to talk to any device of that category. So for instance, you have a standard robot type. And the way this works is that there's a service running on a embedded computer. This is a BeagleBone X15. And this speaks the proprietary protocol to the robot and isolates on a separate network from the main network. And we also do this with ROS and UART2DE and other proprietary networks. And then Robot Raconteur will provide a front end, which is standardized, secure, and able to communicate to a wide variety of devices. And this is how we typically been using it. So we often will put a collection of ROS nodes behind a Robot Raconteur service and then have it available as a standardized type. Now, this can either be done using the ROS bridge or with the bridge specifically designed for the application, so it can have the desired typing for that standard interface. These are example clients. Basically, all I have to do is install the plugin, either Python with pip or MATLAB. There's actually an add-on you can install, or LabVIEW, there's an add-on available. This is it. This is all I have to do to get up and running. And our students come into the lab and they're up and running in minutes talking to a robot. And we found that this is dramatically easier for students to get started with this setup than a pure ROS setup. So there are 3 implementations of the core library. Robot Raconteur Core is a standard library, which is the one which is most mature and most used. There's also 2 forks of interest. One is PyRI, which runs inside a web browser. And the other is Windows XP fork that we use to talk to older equipment. There's also a pure C# implementation, which is used for running inside a web browser. Running inside a web server on mobile frameworks, and also it can be compiled to JavaScript using a transpiler, so you can actually run it in a web browser. So there are 2 ways you can do that, either using PyRI, which is a full Python stack, or a JavaScript version. And there's also a under development ANSI version, which is designed for real-time and minimal systems, and eventually someday safety critical, but that's a really heavy lift. So we'll see when that is possible. So we have standardized service definitions, as I mentioned earlier. We have an abstract robot type, which is kind of like the core capability of a robot. And then we have specific interfaces to talk to the robots themselves. And right now, we're actually working on adding the ability to send motion programs to robots in a hybrid manner, along with EGM external controls. There are 45 standard service type definitions for all different applications and device types and data types, and you can see them all here at this link. There's also a training simulator, which is installed using Conda, based on Gazebo. And this right here has two URI-5 robots, vacuum grippers, cameras, payloads, and there'll be a video later showing this at work. And then we've also just added a mobile robot scene. So this is the demo robot the documentation uses. So now we have a virtual version you can install. And this is installed in a few minutes using Conda. There's very little effort in getting it up and running. Okay, I'm going to move on quickly to the open source teach pendant. So ecosystems like ROS have a lot of very powerful capabilities which are not disseminated and are very hard to use. And there's kind of a disconnect. The robot vendors offer easier programming environments, but have limited capabilities compared to what ROS has. So this goal is to take the technology that's described and create a user interface which can provide a more friendly experience that somebody who's not a highly trained engineer can use. So I'm thinking to my experience with mechanical engineers in my education, what would they be capable of understanding? So these are just some of the requirements. I'm not going to dwell on these too much though for time. This is a block diagram of what the teach pendant looks like. So you have a runtime which manages the system, and then a sandbox where the user programs run. And then there's a front end which can either be on a physical teach pendant or it's on a computer. So it's designed to be used either on a small screen or a large desktop. And then it uses Robot Raconteur drivers to talk to the rest of the system, taking advantage of its plug and play capabilities. So as I said, for ROS, typically what we do is we'll create a front end interface which talks to the nodes in ROS to provide the interface required for this system. And then you have your physical hardware behind the Robot Raconteur drivers or ROS drivers. So we take advantage of a very powerful technology called PyRI I mentioned earlier. And this allows you to compile a fully functional Python stack into a web browser. And this allows us to use a normal Python environment. And this front end for the web for the teach pendant is actually run in a web browser, so you don't have to have any specialized software on your client to use it. And I think I actually skipped over one important point, which is that the program experience uses something called PyRI, which is short for Python Restricted Industrial. It's a modified Python dialect designed to be simpler than normal Python for users who are not that proficient in programming. There are a lot of pitfalls that you can run into. This kind of removes them, makes it easier to program and verify. On top of that, there's a Blockly visual programming environment. So here are some web UI panels. So there's a device list of all the devices the network is connected to, so you can actually do searching for devices, and these are all the standard types which are available for each device. And this is how the user interface knows how to talk to them. There's a jog panel for robots, which allows you to manipulate the robot and save poses. Here is a Blockly program example to pick up objects using markers and then drop them at a certain spot. And here's the same program written in the restricted Python dialect and user interface. So as you can see, the user interface is designed to make it easier to operate on a text language in a touchpad environment. Now, the reason for adding this text environment is that a lot of times moderately experienced programmers will prefer a text environment because it's easier to manipulate and use than a Blockly environment if you're capable of using it. But these are effectively equivalent. This Blockly compiles down to this. Here's an example of the physical teach pendants we developed. So this is here we have the Surface tablet, And then we have a module on the side, which has enabling switches, e-stop, auxiliary buttons, and a space mouse made by the robot. Here's a Raspberry Pi variant of the device. And here is the cabinet, which holds a NUC, which is the runtime computer. So this will live with the system and run the, the programs developed on the Teach Pendant. So here's an example of the Teach Pendant in use. This is our graduate student at RPI. So he's going to create a new blocking program, or show a blocking program that was entered earlier. And then it'll click run, and the robot will execute that program. So there are multiple videos on YouTube of this, and I highly recommend taking a look. And this is actually using vision processing. So here's the preview of the camera and the blocking program running above it. So this is something golden layout, so you can reconfigure the panels here. So this is just a simple demonstration of pick and place. This project is hit pretty hard by the pandemic, so our progress is not as high as we had hoped in terms of the final demonstration. But we're going to try to continue working on it to fully implement the moving conveyor in the future. And here's a simulation of pick and place using the training simulator. As you can see, we have a simulated camera, and this is running the same vision routines on Aruco tags. And this is showing two robots working together to manipulate the parts. So I just want to mention that these projects use Tesseract, which is a SWIRI project for planning. We use it for kinematics, path planning, and visualization, actually also collision checking. So right now, the Tesseract for the PyRI system is actually a separate module. We're merging it in now into the primary robotics modules. So we're using the Tesseract Python wrappers, which are developed by Wason Technology. You can take a look at the link. We use Swig for that. And you can actually install these very easily from PyPy, which is the primary Python package manager, or Conda. So Python comes with PyPy by default, and the installation is self-contained. So you don't have to have any prerequisites. You can just go into Python pip and just install the Tesseract Robotics package. And you can go ahead and try it out now. I wanted to mention, I'm having some trouble with the Conda packages, so please don't just give up. If you have a problem, send me an email and I'll try to help you figure out what's going on. But I encourage you to give it a try. So thank you for listening. And I also would like to thank the ARM in New York State for funding a lot of this development.